Right now, while you're reading this sentence, the sun has already lost more mass than every car, ship, and airplane on Earth combined. Not this year, not this hour, in the last few seconds. It isn't exploding, it isn't dying. It's just quietly coming apart at a rate of roughly 4 million tons a second. And it's been doing that since long before there was a single living cell on this planet. For most of human history, nobody had any reason to suspect this. The sun looked exactly the same every morning. Same size, same brightness. The one fixed point in a sky full of things that moved. That idea was wrong. It was always wrong. In January 2018, a team of NASA and MIT scientists finally proved it, using data from a spacecraft that had already been dead for 3 years, after they deliberately flew it into Mercury. Here's the part that's easy to miss. The sun doesn't lose mass one simple way. It's happening on at least 4 fronts at once, as pure light, as invisible particles passing through your body by the trillions right now, as a violent outward wind, and as gravity itself, quietly loosening its grip. By the end of this video, you'll know exactly how a star can shed a little more of itself every single second and still burn for 10 billion years. You'll also know why, every year, the orbit you're standing on gets a tiny bit bigger. First though, a 200-year-old wrong answer. If you'd asked the smartest scientists on Earth 200 years ago why the sun was hot, they had a confident answer: gravity. The sun, they believed, was a massive ball of gas slowly collapsing under its own weight, and that collapse generated heat, the same way rubbing your hands together warms them up. It's called the Kelvin-Helmholtz mechanism, and mathematically it worked just fine. Except for one problem it couldn't get around. If gravity alone powered the sun, it could only shine for 20 or 30 million years before running dry. By the late 1800s, geologists were already pulling up rock layers clearly hundreds of millions of years old, and Darwin's theory of evolution needed far more time than that to make any sense. Somebody was wrong. It wasn't the geologist. By the 1920s, British astrophysicist Arthur Eddington have had enough of the contraction theory, dismissing it as, in his words, an unburied corpse, a theory everybody knew was dead that nobody had bothered burying yet. So what was the sun actually doing? For a brief, strange window, one leading answer was radioactivity. In 1904, Ernest Rutherford, the same physicist who'd later discover the atomic nucleus, floated the idea that radium, buried in the sun's core, might be the power source. It wasn't a bad guess. Radioactive decay released far more energy per gram than anything else known at the time, but it didn't survive scrutiny. There wasn't nearly enough of the right radioactive material in the sun's spectrum, and its decay rate couldn't stretch to billions of years anyway. Then came the strangest theory of all. In 1917, Eddington floated something that sounds more like science fiction than physics. What if the sun ran on annihilation? What if protons and electrons in its core were simply meeting and erasing each other, converting solid matter directly into radiation? His colleague James Jeans was enthusiastic about it, calling it the obvious mechanism behind starlight. Under that model, a star could theoretically burn for trillions of years. It was elegant. It was also wrong. The real answer came in 1939, when physicist Hans Bethe finally worked out the true mechanism: hydrogen fusing into helium, and calculated a solar lifespan of roughly 10 billion years, a number that has held up ever since. But here's the detail almost nobody mentions. Buried inside Bethe's correct answer was something the annihilation theorists had accidentally gotten right all along. The sun really was destroying its own matter to make light. They just guessed the wrong mechanism. Here's the actual mechanism. Deep in the sun's core, at around 15 million degrees Kelvin, 4 hydrogen nuclei, 4 single protons, fused together in stages to form one helium, 4 nucleus. It's called the proton-proton chain, and the finished helium atom weighs very slightly less than the 4 protons that built it, about 0.7% less. That missing mass doesn't just vanish. It converts directly into energy, following the equation practically everyone's seen scribbled somewhere: E equals mc squared. That single reaction is why the sun sheds an estimated 4.26 million metric tons of mass every second, radiated away as light and heat. Sounds like a raging nuclear furnace, doesn't it? It isn't. This is where things get strange. The very first step of that chain, two protons colliding to begin building a helium nucleus, is almost absurdly rare. Protons carry the same electric charge, so they repel each other hard. The only reason fusion happens at all is a quantum trick called tunneling, where a proton has a tiny minnow-risen chance of simply appearing on the other side of that repulsive wall. Add to that the fact that this specific reaction depends on the weak nuclear force, which lives up to its name, and the result is bizarre. A single proton in the sun's core will sit there, on average, for about 9 billion years before it successfully fuses with another one. 9 billion years for one proton. The only reason the sun produces enough energy to light an entire solar system is sheer numbers. There are so many protons crammed into that core that even a reaction this rare adds up to something enormous. The sun isn't an inferno. It's closer to the slowest possible flame, burning across an almost uncountable number of wicks at once. Fusion doesn't just make light, it also makes neutrinos, nearly weightless particles that barely interact with matter at all. Here's a fact that tends to stop people cold. Light generated in the sun's core takes somewhere around 100,000 years just to fight its way out to the surface, bouncing endlessly through dense plasma. Neutrinos skip that traffic jam entirely. They punch straight through solid matter and escape the sun's core in about 2 seconds. At this moment, something like 1.8 times 10 to the 38th neutrinos are leaving the sun every second. Some of them are passing through your body right now. They always are. For decades, physicists assumed neutrinos had zero mass. Then, in the late 1990s and early 2000s, detectors called the Sudbury Neutrino Observatory in Superpamayokan caught them doing something that shouldn't have been possible, switching identities mid-flight, shifting between different neutrino flavors on the trip from the sun to Earth. That kind of shape-shifting only works if neutrinos carry some tiny amount of mass. It solved a decades-old mystery known as the solar neutrino problem, and it earned a Nobel Prize. Which raises a question almost nobody thinks to ask. If neutrinos have mass, and the sun is firing off more than 100 trillion of them every second, isn't the sun losing actual matter, not just energy? Through particles that will likely never touch anything else again? Physicists still don't know a neutrino's exact mass. They only know it's absurdly small, with just an upper limit from cosmology to work from. But using a reasonable estimate within that limit, the math suggests the sun could be shedding somewhere around 10 kilograms of real mass every second, purely through neutrinos. Actual matter, just in a form that will probably drift through the universe forever without ever hitting anything again. Fusion is only one piece of this. The sun also physically throws material outward as the solar wind, a constant stream of charged particles blasting off its surface at hundreds of miles per second. That adds close to another 1 to 1.5 million metric tons of mass loss every second, on top of whatever fusion is already taking. To find out exactly what the solar wind is made of, NASA sent a spacecraft called Genesis out to a gravitational balance point between Earth and the sun, specifically to catch solar wind particles and bring them home for study. Hardly, measuring hydrogen, the simplest, most common element in the solar wind, wasn't even part of the original plan. It was considered too technically difficult. Researchers eventually pulled it off anyway, and what they found reshaped how scientists think about the sun's atmosphere. The sun doesn't fling every element outward equally. It behaves almost like a filter, favoring elements that ionize more easily and holding others back. But the solar wind isn't always steady. On one specific day, it nearly vanished. On May 11, 1999, satellites recorded the solar wind's density collapsing to less than 1/10 of a particle per cubic centimeter, essentially nothing, for more than a full day. Researchers still call it the day the solar wind almost disappeared. Without that constant outward pressure, Earth's protective magnetic bubble did something it almost never does. It swelled. Earth's bow shock, where the solar wind normally slams into our planet's magnetic field, usually sits somewhere around 10 to 15 Earth radii out. During this event, it ballooned out to nearly 60 Earth radii, close to the moon's orbit. Auroras vanished. The entire shape of near-Earth space temporarily reorganized itself. Nobody has ever fully explained why the sun briefly held its breath that day. It's one of the clear reminders that even the steady parts of its mass loss aren't steady at all. Add up fusion, neutrinos, and solar wind, and the sun is losing a genuinely staggering amount of material every second. And yet across a human lifetime, across all of recorded history, its gravity has never seemed to shift even slightly. That's because the effect, while real, is almost unimaginably small at human timescales. The sun's total mass is so enormous that even millions of tons a second amounts to losing only about a 10,000th of 1% of its mass across 10 billion years. Almost unimaginably small isn't the same as zero though. And in 2018, scientists finally measured it directly. Basic orbital mechanics says that if the sun's mass keeps shrinking, every planet's grip should loosen slightly, and every orbit should widen, gradually, the same way a figure skater drifts outward the instant their spin loses momentum. For Earth, the math works out to about 1.5 centimeters a year. For Jupiter, farther out, it's closer to 7 centimeters. For Neptune, way out at the edge, more than 40 centimeters a year. For a long time, those were just numbers on paper, predicted but never actually observed. Then researcher Antonio Genova, working with NASA and MIT, had an idea. NASA's Messenger spacecraft had gathered 7 years of ultra-precise tracking data on Mercury, first during a handful of flybys, then during years spent actually orbiting the planet, before it was deliberately crashed into Mercury's surface in 2015. Mercury sits deeper in the sun's gravity well than any other planet, which makes its orbit unusually sensitive to the tiniest shift in the sun's pull. Genova's team combed back through that tracking data and found it, a measurable shift in the sun's gravitational parameter, changing by about 6 parts in 100 trillion every year. It doesn't sound like much, but it lined up well with what physicists expected from the sun's ongoing mass loss, and for the first time, someone had measured that shrinking directly, instead of just calculating it from theory. As a bonus, the same dataset let the team test one of the deepest ideas in physics, Einstein's strong equivalence principle. It held up. A dead spacecraft, tracking a planet, ended up confirming something about the nature of gravity itself. Here's a genuine twist. While the big planets get pushed outward as the sun loses mass, the smallest objects in the solar system, asteroids and dust, can get pulled in exactly the opposite direction, by forces that have nothing to do with gravity at all. Take the Yarkowski effect, named for a Polish engineer who first described it in 1901. An asteroid absorbs sunlight on its sun-facing side, then hours later, as it rotates in the shadow, radiates that heat back out, similar to pavement staying warm long after sunset. Because the asteroid keeps spinning, that delayed heat release pushes gently in one consistent direction, an incredibly weak, incredibly patient thruster. NASA got to measure this directly during the OSIRIS-REx mission to the asteroid Bennu. The force involved was tiny, equivalent to the weight of about 3 grapes pressing continuously against a rock 1/3 of a mile wide. Over time, though, that whisper of a push has shifted Bennu's orbit by close to 284 meters a year. It's the same effect that likely dragged Bennu out of the asteroid belt millions of years ago and onto a path that now brings it uncomfortably close to Earth. Meanwhile, at an even smaller scale, something called the Poynting-Robertson effect does roughly the opposite job. Dust brains orbiting the sun get struck by sunlight at a very slight forward angle. For the same reason raindrops seem to hit a moving car's windshield, even when they're falling straight down. That subtle forward push acts like a brake, slowly draining the grain's orbital energy and dragging it inward toward the sun. It's a big part of why somewhere between 2,000 and 100,000 metric tons of interplanetary dust rain down into Earth's atmosphere every year, mostly as invisible micrometeorites. The sun's mass loss pushes the big worlds away. Something close to the opposite drags the small stuff in. So where does all of this actually lead? Even adding up fusion, solar wind, and every ghostly neutrino, the sun will only lose a small fraction of its total mass across its entire 10 billion year life as a stable hydrogen-burning star, well under 1/10 of 1%. On any human timescale, and honestly on almost any timescale that matters to us personally, the sun isn't going anywhere. The real drama comes much later. Billions of years from now, once the sun exhausts the hydrogen in its core, it will swell into a red giant and start shedding its outer layers in earnest, eventually losing something close to half its total mass before what's left collapses into a small, dense ember called a white dwarf. That's the ending stellar physicists actually expect, slow and steady for 10 billion years, Then one last, dramatic exhale. That's a story for a different video though. What's true right now is smaller and somehow stranger. The sun you saw this morning isn't the same sun, atom for atom, that anyone saw 100 years ago. It's a little lighter. Its pull on every planet, including the one you're standing on, is a hair weaker than it used to be. Earth's orbit is very slightly bigger than it was when your grandparents were born. Nothing about this solar system is actually fixed. Not the sun, not our distance from it. It's all drifting, one careful centimeter at a time, and until 2018, nobody had direct proof of any of it. If this kind of hidden, slow-motion physics is what fascinates you, that's exactly what we dig into here at Cosmos Coastline. Subscribe if you want to keep exploring the parts of the universe moving too slowly and too quietly for anyone to notice on their own.